Welcome to Chapter 9. In this video, we'll derive the equations for the inverse base p trig functions, and on the way, we'll solve a previously unsolved integral. We'll start with inverse sine base p, or arc sine base p, and discuss what properties I want it to have. The first is probably the most obvious. Sine base p of arc sine base p of x should be x. The functions should essentially undo each other when they're composed. The second property is that since sine base p takes values from -1 to 1, arc sine base p should only be defined for x values between -1 and 1. And for the third property, since the first strictly increasing or decreasing interval of sine base p happens on this interval, arc sine base p should have a range of -pi/2 to pi/2. In order to get this formula, what we're going to do is call arc sine base p of x y. We'll take the sine of both sides so that it's in a form that we can differentiate. Then we'll rearrange it into a form we can integrate and then turn back into arc sine base p. So starting with sine base p of y equals x, we'll differentiate both sides with respect to y. Then we'll move a single cosine down and multiply the left by cosine base p over cosine base p. We can get rid of the absolute value in the denominator and consolidate everything, keeping the terms separated on either side of the fraction bar. It's clear to see that the hype squared term will cancel with factors in the denominator, and we'll also replace the y's in the numerator with arc sine base p of x's. Now to rewrite this in a simpler form, we're going to use a p-norm triangle like in Chapter 7. The sine of the angle y is x over 1, and that makes the final side 1 minus the absolute value of x to the p all to the 1 over p. Using this, we can find cosine base p of y and rewrite our numerator like so. I also made that reciprocal of cosine squared a secant squared. Now that it's in this form, we're ready to separate and integrate. The left side is a commonly memorized trig integral that comes out to tangent, but the other integral is a completely different case. I have in my script that I have to get hype because this is an integral that was unsolvable until now. So I'm getting so hype that I got a base p. And this, my friends, is our first example of an integral solvable with a base p trig sub. Yes, it's very exciting. So let's begin. We'll have x equals cosine base p of theta and dx equals its derivative d theta. Ignore the mild abuse of differential notation. This still works if we keep p constant. Let's perform the substitution and simplify. Real quick, let's check out the signum sine theta. Since x is cosine base p theta, then theta is arc cos base p of x. Following the same line of logic we used for defining domain and range for arc sine base p, we'll find that arc cos base p, or theta, is between 0 and pi. Since on that interval sine is between 0 and 1, signum sine theta is just 1. So our integral here just becomes the antiderivative of negative cosecant squared, which is another commonly memorized trig integral. To finish our base p trig sub, we have to get this back in terms of x, which we can do with another triangle. This turns cotangent of arc cos base p of x into this whole thing. There's an asterisk that since arc cos base p is only defined for x between -1 and 1, that this expression with a larger domain has to be restricted in the same way. So replacing our cotangent theta in the full equation, we can now solve for y. The final thing we need to do to define arc sine base p is solve for the constant of integration, which is easy for this problem. Since sine base p of 0 is 0, arc sine base p of 0 is also 0. That means when we plug 0 in for x, y should also equal 0. Arctan of 0 is 0, therefore c is 0. Now we have an expression for y, and because we first defined y as arc sine base p of x, it follows from the transitive property that this is the definition of arc sine base p of x. Now let's define 3 more inverse trig functions. Arc cos base p is the same as arc sine, but with an arc cot instead of an arc tan, and this is also equal to pi/2 minus arc sine base p of x. Arccosecant base p has a slightly different expression with the arctan, but it is equal to arcsine base p of 1 over x. And finally, arcsecant base p, which follows the arctan arccotangent pattern and is equal to arccos base p of 1 over x. At this point, you might be wondering about the inverse of hype. Sadly, I don't have an expression for this function, but here's a little information about it. Its range should be from y equals 0 to pi over 4, and its domain is a little complicated. If p is greater than 2, the domain is from 1 to 2 to the 1/2 minus 1 over p, and if p is less than 2, it's the opposite. If you're interested, please comment down below what you think may work for solving this, or if you did find a solution. Anyway, here we have 4 inverse trig functions, and they look quite nice if I do say so myself. As a final note for these, you'll notice that I did label these functions with the prefix arc, and unfortunately, these do not return the arc length of their own p-norm squircles, unless p equals 2, of course. I find the -1 notation to also be acceptable, but the reason I used arc is because that will be consistent with their function names in Desmos. And speaking of Desmos, I'll add the inverse trig functions to the squircular coordinates graph in the comments under this video and chapter 8. Okay, bye.